So let us discuss in this lecture correlation type demodulator. You understand the function of signal demodulator. Signal demodulator function is to convert the received signal R of t into received vector R. So let us discuss correlation type demodulators. Okay, working principle. It decomposes the received signal R of t and noise n of t into n-dimensional vectors. Because you received signal Sm of t plus n of t, capital in the dimension of waveform Sm of t. Okay, so correlated type demodulator consists of a parallel bank of n correlators, cross correlators. So these things can be, in the other words, signal and noise are expand into a series of linearly weighted orthogonal basis function, because Sm of t, if it is n-dimensional as a transmitted signal, so this can be written as sum of Smk into Fk of t. Fk of t is the basis function for this. Okay, so if I will draw the block diagram of correlation type demodulator, this is your R of t is a received signal. We are assuming that it is n time. This is Sm of t plus n of t, and dimension of this Sm of t is a capital N. So there will be n branch, 1, 2, and capital N branch. So each branch received signal will multiply with the base vector f1 of t. In this branch, there should be multiplication of received signal with the capital N basis function in each branch. S1 of f1 of t is multiplied in this branch, f2 of t multiplied in this branch, and so on. In this branch, nth branch, the basis function is fn of t. Okay, and then pass through this integrator. You have to integrate the r of multiplication of rt with fk of t, where k varies from 1 to capital N, and then you have to integrate this is. So this will be equivalent to the finding the inner product between R of t. Recall the definition of inner product between this Fk of t. So actually, up to here, we are, what is the function? Decompose. We are decomposing the received signal R of t. Means I want to find the capital N projection of received signal on each basis signals. Okay, okay, so these things are written. Sm of t can be written like this. Remarks on noise. In the case of noise, basis function Fk of t don't span the signal. Noise don't span the noise space, because white noise n of t has infinite bandwidth, so it has infinite number of dimensions. So for noise, capital N subscript n is the dimension of noise n is infinity. But Fk set has a finite. So we want to say that this set cannot represent noise space. Okay, so it cannot be represented n dimensional space discussed earlier. However, we can show that noise terms that fall outside the signal space are irrelevant to detection of the signal. Suppose capital N is a 10, so there is 10 dimensional signal. But we know that noise has infinite dimensions. So noise present in 11th onward dimensions are not relevant for the detection purpose of the signal. Because what is the noise present in first 10 and 10 dimension of the signal space is relevant for detections. Okay, so correlation type demodulator consists of a parallel bank of n cross correlator which basically compute the projection of r of t on the n basis vector as illustrated. So this is a inner product of RT with basis vector basis function f of f subscript k of t. Okay, so this inner product between this is represented by small r subscript k. Okay, so if we'll do this, so this sm k of t will be this, nk will be the inner product of noise nt with the kth basis signal, and this is also smk will be the inner product of sm of t on the basis with function fk of t. Okay, so k varies from 1 to capital 1, so vector form representation rk equal to smk plus nk. Okay, for k is equal to 1, this is r1 sm1 plus n1, k equal to 2 r2, this is r1 r2 sm m2 plus n2, and so on. For k equal to capital N r subscript capital N, this is sm n plus n subscript capital N. In vector form I can write like this, r1 r2 in matrix form means column vectors, n1 n capital N n2 okay. So vector form representation of the equation 5, this is collection of this, Uh, so where capital N is boldface R is this vector, boldface SM is this vector, boldface N is this vector, where Nk are random variable that arise from the presence of additive noise. In fact, we can express the received signal RT in the interval like this. We want to show that the noise outside the n dimension are irrelevant for the detections. So Sm of t can be written as in summation form, linear summation of fk of t. Similarly, nk first n dimension projection of noise can be written like this, and n hat of t is the remaining noise signal. So this n hat of t is defined like this: nt minus the first capital N projections of uh, representation of noise in first capital N dimensions. Okay, so n hat is also a zero mean Gaussian noise process. It can prove n hat of t is irrelevant to decision as to which signal was transmitted, because decision may be based entirely on the correlator output signal and noise components. Okay, these noise uh, components are irrelevant for decision. Okay, so noise component are Gaussian random variable. Okay, so calculate the mean and variance of this, a mean and covariance. So at nk is the projection of noise nt on the kth basis vector. This can be written as in integral form n of t into fk of t. Okay, so I will take a statistical average of this nk. So I will take this one. I will take expectation inside of the integration. So this expectation of nt, because nt is a Gaussian noise of zero mean. So mean expectation of nt, fk of t is a deterministic signal. Deterministic nature. Fk of t. So expectation n of t is a random signal, random nature. So expectation of this nt will be 0 for all k. So we can show that the mean of nk is 0. Let us calculate the covariance. Means covariance means mean is 0, so covariance will be a joint expectation of nk and mn. Okay, so integral representation of nk and mn are like this: fk of t and tau. They are two dummy variable t and tau t. Okay, so I will take expectation inside. So expectation of n tau, because noise is, so this is expectation of nt with n tau, can be written as n naught by 2 del t minus tau. Okay, this is joint expectation of Gaussian noise. Okay, so I will rearrange and change the order of integration. First, I will do the integration with respect to tau. So I del tau minus t into fm tau. Okay, okay. So result will be fm of t, because if you are integrating del tau minus t naught with a signal d tau, result will be the f t naught. Okay, so that's why we are getting Fm of t dt. So note that Fk and Fm are orthogonal basis signal. It means when k equal to m and not equal to m, so orthonormal. Orthogonal means orthonormal means the inner product of Fk. This is equal to this integral equal to inner product of Fk of t with Fm of t. Okay, and this can be written in 0 when k equal to not m, because k are not equal to m means they are orthogonal, means the inner product should be 0, and it is orthonormous, then k, when k equal to m, then it will be norm should be the unity. Okay, so using these things I can write, because you have to multiply with n naught by 2, I can write like this. Okay, where this can be written like this: covariance. This is, here delta is a Kronecker delta function. Okay, so we have calculated mean and covariance of the noise component nk. So now we have this result: mean is 0 and this is covariance. So when k equal to m, so I will get the expectation of nk square. This is variance, because mean is 0, so second moment will be the variance. So this will be equal to n naught by 2. So it indicates the n noise component are 0 mean uncorrelated Gaussian random variable with the common covariance n naught by 2. For each noise component, the mean will be 0 and variance will be equal to n naught by 2. So let us write the joint PD of n noise components, because n is the vector of capital boldface, n is a vector. Okay, these are independents. So joint, this is joint PDF of the vector n will be the product of joint PDF of the vector capital n will be the product of PDF of each components. So that can be written like this. Okay, so f, this n is a normal ni. This can be also represented like this: 0 mean and variance n naught by 2. So if I will write the PDF of ni, that will be square root 2 pi sigma square will be n naught by 2, exponential mean is 0, so ni square divided by 2 sigma square, that will be n naught, and after simplification we can write this is PDF of f ni. This is 1 by square root pi n exponential minus ni square divided by n naught. Okay, so if I multiply exponentials, so I can write like this. So capital N, this is common, so multiply n times, so the power will be n by 2 in this constant pi n naught, and exponential can be multiplication of exponential can be written like this. So now we know that what is the statistical characteristic of nk, random variable. Nk is random variable. Okay, so what is the mean and their joint PDF and their covariance, which we know. Okay, so if you are adding a random variable deterministic component Sm k of t, So this rk will be also a random variable. So from previous development, it follows that correlator output rk condition on mth signal being transmitted are Gaussian random variable with the mean like this. Okay, if you're adding a Gaussian random variable with a constant, a deterministic quantity, I will get the Gaussian random variable. So this is mean of rk random variable. So expectation of substitute rk is smk plus nk. So take expectation inside. So I will get expectation of smk plus expectation of nk. Because smk is a deterministic nature, so expectation of this symmetric signal will be the deterministic signal. Yeah, Nick. Okay. Now expectation of nk, we know that nk is a Gaussian random variable with zero mean. Okay, so mean will be 0. So now mean of the rk will be the smk. Okay, let us calculate the variance. Sigma rk square. So I will calculate expectation of rk into mu rk. Okay, so I can write like this also. Substitute rk, because we can write variance, it can be calculated also like this. Okay, using this I'm writing this. Okay, now substitute rk is smk plus nk square. I will get this. Take expectation inside operator, mu square of mu rk will be the smk square. Okay, so I will write like this. So expectation of square of smk is a deterministic nature. So square of this smk, the 2, because it's deterministic, so it is taken outside. So expectation of nk, this is 0. I'll substitute expectation of nk square, that is a variance n naught by 2. Substitute these value. After simplification, this will cancel out. This will be 0. Now you will get this is n naught. So this is a variance of this of random variable, conditional random variable rk. So this random variable also is a Gaussian nature, but mean with smk and variance n naught by 2. This is notation for the normal or Gaussian random variable. Okay. Since noise component are uncorrelated Gaussian variables, they are also statistically independent. This is exception, because if random variable is uncorrelated, it doesn't always indicate that it is independent. But in case of only Gaussian, uncorrelatedness indicate the independence of the random variable. Okay. So as a consequence, correlator output rk condition of mth signal being transmitted is statistically independent Gaussian random variable. So what is the joint PDF? Because random variable are analyzed or characterized by their joint PDF mean and variances. And Gaussian random variable is fully characterized and specified by its mean and variance. Okay. So hence joint conditional PDF of random variable are simply can be written as this vector R. So product of conditional PDF of R, conditional random variable RK given SMK. Okay. So this PDF can be written like this, because mean is this and variance is sigma square equal to n naught by 2. So this is Gaussian PDF expression we can write. So this is joint PDF of random variable R, random vector, not variables, sorry, vector R, because vector R is a collection of capital N random vectors, random variables. So this is joint PDF of random vector R. It is written as a, because independence, so uncorrelated means independent, Gaussian noise uncorrelated means independent Gaussian random variable. So joint PDF will be the multiplication of individual PDF of the random variable. This is a joint conditional PDF. So it is a joint. This is PDF of conditional RK given SMK. Okay. Substitute this 16 into 15. After simplification, I can write like this, and this can be also written in this vector form, because I can, this is vector R is this, vector SM is this. If I will subtract this, I will write this R minus SM1, R2 minus SM2, and so on. R substitute capital M minus SM N, like this. If I will write the norm square of norm, so that will be the sum of square of each component in this vector. This, so after simplification, I can write like this. This summation can be equivalent to this. So this is joint PDF of a random vector R. Give a conditional joint PDF of vector R given vector Sm. So we have written like this. Okay. So now we want to know that the sufficient statistics. So our objective is to show that correlator output vector R are sufficient statistics for reaching a decision on which capital M signal was transmitted. We means we have sufficient number of information to take decisions. That means no additional relevant information can be extracted from remaining noise process, that is defined as a n hat of t. So indeed, how I can show that n hat of t is uncorrelated with n correlated outputs. So I will say that because if n hat of t remaining noise is uncorrelated with this correlator outputs, so I can say that this n hat is irrelevant for the decision making. Okay, so first uncorrelated means I have to find the covariance, joint expectation. Okay, so covariance, because n hat of t is a zero mean, so covariance will be the, because this is x mu x, this is covariance between random variable this can be equivalent to the joint expectation of mu x and mu y, because one random variable mean is 0, so this term will be 0. So covariance will equal to this. So now n hat of t is this, rk is this, rk can be written like this, multiply inside, so I will get this one, take expectation inside, sm of k is a deterministic nature, so it will be a scalar, a constant, so it will come outside. So now expectation here will this, and here expectation will this. Okay, because mean of this n hat of t is 0, so this term will be 0. Now we have this, we have to find what is this expectation of n hat of t with nk. N hat of t is nt minus this projection of noise nt on the n basis vectors. Okay, a basis signal fj of t. So multiply this, so this will be this and this will be this. Take represent nk will be in integral form this. Okay, take expectation, so this after simplification we can write like this. Take expectation inside, so I will get this one. Okay, take expectation inside here, I will get this one. Okay, so because this summation j equal to 1 to n expectation of nj into nk with fit. Okay, when j equal to k, this will be n naught by 2. So this will be when j is equal to k, when j vary from to capital N, when j equal to k, so this will be expectation of j equal to k means nk square, and this fk of t, this term will with it. So this when j equal to not k, so this expectation of nj with nk joint expectation will be 0, and this will be n by n naught by 2. Okay, so I can write like this, summation will disappear, only this term will be appear because remaining term will be 0 because due to this uncorrelated. So I can write like this. Now we know that this expectation of nt with n tau can be written as n naught by 2 into del tau minus t. Here del is a direct delta function. Okay, we multiply and we using my direct delta function property, this will be the, after integration I will get fk of t. Okay, substitute and this will give this. So this shows that n hat of t and this random rk, random variable rk, are Gaussian uncorrelated. They are also statistically independent. Okay, consequently n hat of t doesn't contain any information that is relevant to decision to which signal waveform was transmitted. So correlated output are sufficient statistics for making decision. So all relevant information is contained in the correlated output, hence n hat of t may be ignored for the analysis purpose. For this lecture I am taking material from this book. You can refer this books. Okay, thank you for watching the lecture.